What we did in the last class, we have seen or we have discussed that we can use the operation amplifier in negative feedback, right? Negative feedback configuration, and that would make it useful, correct? What was the feedback gain of what we did last time? Voltage series, right? There are four type of feedbacks possible. It's a very general concept, right? Negative feedback concept is very general, right? So you can use it for the op amp. So if we use voltage series feedback for op amp, what was its feedback gain? Feedback gain was 1 plus RF by R1 for the ideal conditions, right? When AR1 was far greater than R1 plus RF. So this is what we derived here, right? Here. V naught by Vs is our gain. I think we lost that slide. So V naught by Vs, right? Output divided by input. And the answer was A R1 plus RF divided by A R1 plus R1 plus RF. This is the exact feedback gain of your op amp, right? For ideal condition, when your AR1 is greater than R1 plus RF, because for ideal amplifier, AR1 is quite large, right? A value is quite large. Subsequently, AR1 would be large, so AR1 would be greater than R1 plus RF. And therefore, AF ideal would be 1 plus RF by R1. And this is what we generally see in your lab manual and your previous classes might be. There is one more concept of gain of feedback circuit, right? We are studying feedback, negative feedback. So what is the gain of feedback circuit? How would you define that? Gain means output divided by input, right? So feedback, the output was, for the feedback circuit, the output was Vf and the input was V naught. So Vf by V naught, this is how we define gain of your feedback circuit. This is a very important parameter and you will see it in the later slides. So in order to evaluate your feedback gain of the feedback circuit, Vf is R1 divided by R1 plus RF into V naught, right? We have seen it in the previous class. You can write your feedback gain as R1 divided by R1 plus RF. This is a very important parameter which will help you in solving the numericals. B is equal to R1 divided by R1 plus RF, where R1 is your resistor, right? Input resistor we bolte. We also call it input resistor, feedback resistor, right? In ideal scenario, what would happen? See, from here and from here. This is AF ideal. B is 1 upon AF ideal. Correct? Just we can ask one more question, right? That what is the relation between B and AF for the ideal condition? Next, what target is, or the question in hand is, express the exact closed loop voltage gain AF in terms of open loop gain A and feedback circuit gain B. We have just defined or we have just obtained the feedback circuit gain, right? That is B. And we know that the open loop gain of op amp is always given to you. So one might ask you, what is the closed loop voltage gain AF in terms of A and B. Ideal conditions we have seen. For the ideal condition it is okay, but exact, right? So AF exact is, if you remember, A R1 plus RF divided by A R1 plus R1 plus RF. We have derived this here. This is the expression, equation number 1. AF exact is given to us from 1. Now what we will do, this is in numerator, right? R1 plus RF is in numerator. So we will take it in the denominator of the denominator, right? So it's a very simple process. After this manipulation, you can see that this quantity will become, this term will become 1, and this term is R1 divided by R1 plus RF, which is B. Correct? So AF exact is A divided by 1 plus AB. In your textbooks, many times you see this expression. Correct? If I change my R1 value or RF value, which of these parameters would change or quantity would change? Capital B. And that will change your AF. Correct? Okay. So this was a concept of evaluating your AF exact in terms of A and B, or in terms of R1 and RF and A. What I mean is this equation number 1 and this A upon 1 plus AB. But if you are only interested in ideal scenarios, there is a shortcut method, right? Do you remember that shortcut method? That I will discuss. That for ideal amplifier, first you prove that this is a statement, right? I am making a statement. For ideal amplifier, difference in voltage is 0. Okay? And by using this statement, or by using this logic, find out AF ideal. Right? This is the task. Correct? So VID is V naught by A, because V naught is VID into A. And for ideal, because we are saying ideal and we have discussed various characteristics of your ideal amplifier, ideal means A is almost infinite. This would imply that your VID is almost 0. Our first statement is true. We have proved it, right? By using this VID is equal to 0, we can write the voltage at V1 or inverting terminal and non-inverting terminal are equal. V1 is equal to V in for the same configuration, feedback configuration. See this figure, right? So this is your V1. Positive terminal, at positive terminal we call V1, and voltage at the negative terminal we call V2. Not negative means inverting. V in is equal to Vf, and Vf was R1 divided by R1 plus Rf into V naught. Correct? From that, you see that AF is 1 upon Rf plus R1. AF ideal is V naught by V in, which is equal to 1 plus Rf by R1. So the motto of showing you this result, discussing this, was that in most of the text and in your previous classes you have seen this. That is why you were unaware of the fact that AF exact is AR1 plus RF divided by AR1 plus R1 plus RF, because you have used these steps most of the time in order to derive the feedback gain, voltage gain with feedback. Agreed? You might not have seen this, right? AR1 plus RF divided by AR, this formula, right? Now you see that this condition is true when you only consider the ideal scenarios. Most of the time it is true also that AF ideal will be quite close to AF exact, right? Because 10 to the power 5 is quite large. Anyway, next question is, what is the input resistance with feedback? Exact. We are not considering the ideal conditions, the exact. कैसे निकालेंगे? How would you do that? So this is the diagram of your voltage series amplifier, right? Voltage series feedback with using an op-amp. Do you agree or not? This is same, right? Here we are interested in deriving the input feedback resistance or input resistance with feedback. What is the definition of your feedback input resistance? Input voltage divided by input current. So you can see that this is your input voltage, correct? Because this is the only input you have, right? Is available to you, and I in is the current which is going inside, right? So V in divided by I in, and I in is VID divided by RI. What is VID? VID is the voltage across the input resistor, because this is the input resistance without feedback, right? Correct? This is the circuit or equivalent circuit of your op-amp, open loop op-amp, only this part, right? This part. Correct? Now you are asked what would be the input resistance of this circuit, this box, right? Because when we discuss about the input resistance and output resistance, we just see the whole circuit as a box, right? What is the current going through it when we apply some voltage? Voltage divided by I. This is how we find out the input resistance. We don't care about the internal block, right? So first, with open loop, we have seen this. We have derived Ri, 2 beta, AC or Re, something like, right? Something like that. 2 beta, I don't remember. So now, for this a new configuration, what is your input resistance? The input you apply, the voltage, input voltage you apply, and there's a current that goes into the circuit. So this is how you can. So this is your step B, that your I in is differential input, right? Divided by Ri, and your input resistance with feedback is input resistance without feedback, Ri multiplied with V in divided by VID. Next we have to see, because our aim is to find out RIF in terms of Ri, A and B. A is your open loop gain, B is your gain of feedback circuit, and Ri is input resistance of the open loop amplifier, right? V in divided by VID, okay. Now our aim is to put terms A and B. VID is this, correct? Exact की बात हो रही है. So RIV in A by V naught. You can arrange it. It will become Ri into A multiplied with V in divided by V naught, right? And this is what was your feedback gain? Correct? Not feedback, closed loop gain, right? Closed loop gain. We should call it closed loop. Otherwise, you will get confused with B. B is a feedback circuit gain of the feedback circuit, and AF is closed loop gain. You can also change it if you want, AC, right? It's a closed loop gain. So AF, if you remember, what was your AF in terms of A upon 1 plus AB? AF was A upon 1 plus AB. So your input resistance with feedback is Ri 1 plus AB. Correct? Or this is the voltage gain with feedback. Input resistance with feedback is higher than the input resistance without feedback. This is exact, right? There is no assumptions, right? Similarly, can you evaluate output resistance with feedback? If you have any doubt till now, please ask. What we have done, we have derived AF exact voltage gain with feedback, exact formula, right? Not ideal. In terms of A and B, and the answer was AF is equal to A upon 1 plus AB. So of course you can see that AF is less than A. Next, we also discussed a shortcut method to derive the AF ideal, right? And what concept did we use? We used the fact that the difference input voltage is zero. I mean, because of the high open loop gain of the amplifier. Then we have discussed what is the input resistance with feedback, and the formula is input resistance with feedback is 1 plus AB times input resistance without feedback or open loop feedback input resistance. So we have seen A is a open loop voltage gain, B is feedback circuit gain, AB there is also this parameter, right? 1 plus AB, right? AB is called loop gain. Loop gain. Okay, just also notice this circuit in controls. Have you studied control system? Not yet. Okay, so this is your A. Correct? This is your amplifier A, and you are providing VID to it. And you are taking some part of V naught. You are taking almost each part, and you are giving it a circuit, feedback circuit, whose gain is B, which you have derived. So this is your V naught, and this is your VF. Input-output relation of each block you know, right? This is also called block diagram representation of non-inverting amplifier with feedback. So you can see that you can easily evaluate V naught by V in by just observing this. But now VID is V in minus VF. V naught is A times this, which is equal to VF. Correct? A times V in minus VF is this, and B times V naught is equal to VF, and this is your V naught, right? So you can equate it, and you can see that answer will be this only. So in controls, you will see this circuitry. So it is just for the sake of completeness, that is how we represent the feedback. Or this is the block diagram of feedbacks. In controls, when you know that each of the block has some gain, right? Now you know that each of the block has some gain. This is just for you, these blocks are just a amplifier with some gain, right? So you can just replace those circuits, feedback circuit with this and op-amp with this. This is not the equivalent circuit, right? Don't confuse it with that. Equivalent circuit was this. Correct? Equivalent circuit is this. But now you have seen that this block is nothing but a amplifier with gain B, and you can see that this is nothing but something which gives the output, which is A times V ID, right? So just okay, don't get confused. Just ignore it for now. Okay? When you will study control systems, now it will become more clear to you. You might have the course, right? Next semester में या फिर जब. Yes, so this will be your home assignment that you need to please try to do that, and the answer is in the book, so you can take help from the book. What is the output resistance with feedback in terms of output resistance without feedback, or open loop output resistance, open loop voltage gain, and gain of the feedback circuit. We have discussed this bandwidth, right? Bandwidth concept with a feedback, but there we have assumed that AF was ideal. So the same concept we can use with the exact value of AF, correct? So gain bandwidth product is constant. Okay. You can also equate this term as unity gain bandwidth, correct? How? A is a gain, this is your bandwidth, correct? So this term, when you equate A equal to 1, the whole term will give you unity gain bandwidth. The value of the bandwidth when your A is 1. So these all terms are equal to unity gain bandwidth, just for this knowledge. So yes, what would be value of your bandwidth with feedback? It will be original or open loop bandwidth multiplied with 1 plus AB. You can see that this factor is coming a lot, right? So it is better always when you solve the numericals, you just evaluate this value, 1 plus AB, right? This is a fact, right? Your input resistance is K. I mean, your input resistance get multiplied with this factor. Your output resistance get divided by this factor, right? Your voltage gain get multiplied with this factor. This is, I hope you have studied in your practical classes, right? Frequency response of op-amp. In previous class, I just did this. This is a general concept of bandwidth, but the frequency response of your op-amp would not look like this. Can anyone give the reason? नहीं, log की बात नहीं है. I told you that this circuit is blocking DC, right? The frequency response, the circuit or the device whose frequency response is this, it is blocking DC. But our op-amp does not block DC, right? It passes DC. It also passes the low pass content of your frequency. This is a band pass filter type of system, no? This is a band pass. Band pass filter means it passes a band of frequency and blocks a particular part and then blocks a particular part, right? This is called band pass. You might have studied it, no? No? Filters? You never studied filters? Anyways, so low pass filters are the filters which allows low frequency and blocks the higher frequency after some cutoff frequency. Op-amp is such a system, right? Such a device. So its frequency response is something like that. We'll discuss in detail. So just what is your UGB? This is your unity gain bandwidth, right? When your gain is 1. And you can see that I told you the bandwidth of your open loop gain is very small. 2 to the power 10 to the power 5, right? 2 to the power 10 to the power 5. And only it will allow only the, what was the bandwidth? Batao? The band of frequency over which your gain was constant. So for the open loop configuration, you will see that this is gain and this is your bandwidth. If you want lesser amount of gain, then your frequency response would become something like it, right? Up to 1 megahertz, it will give you gain of 1, right? So this is what we do with the feedback. We are decreasing the gain and we are increasing the bandwidth. Yes, this is one more parameter. Total output offset voltage with feedback. What happens to this parameter? What was the output offset voltage? When there is no input, due to mismatch, there will be some VID. There will be some voltage across your RI. See, this is your equivalent resistance circuit, equivalent circuit of voltage series feedback, correct? Even when your V in is 0, there will be some VID, due to which you will get some output. So for open loop configuration, you will get this gain, this output, correct? But now you have applied feedback, so the output, at the output you will get this, correct? If you divide, what will you get? That offset voltage with feedback decreases, correct? It is a desirable quality, right? You can now adjust offset null use करके, you can remove it, na? So one special case of op-amp with or op-amp in non-inverting mode. This is op-amp. We have studied op-amp with voltage series feedback, which is same as or also known as non-inverting amplifier, correct? Now one special case of non-inverting amplifier is voltage follower. When we set our AF equal to 1, then your V0 will be equal to Vin. This is called voltage follower, because your output is following your input voltage. So one such, one way to do that is, because your AF is 1, we are assuming the ideal scenario. If you put RF is equal to 0 and R1 is equal to infinite, then RF is 0 means you have to just wire your output with the negative terminal. There is no resistor, no RF. And R1 is equal to infinite means you have to open it, right? This part. So it is like that. So you can just, so this is the voltage follower circuit. But how is this clear?
What is the need of voltage follower?
We'll see it later. Current gain वगैरह के लिए या फिर कुछ करने के लिए हो सकता है, या फिर for example this is input and you want to put something which has very high resistance so that there is no loading. You want, there is some input signal which is coming from some circuitry, right? तुमको isolate करना है. Next stage is some circuit. You want to isolate these two circuits so that there is no effect of loading. There is no effect of this circuit on this. So there should be a very high buffer. It should be buffer, but very high input resistance. Something which will isolate both these stages. Op-amp isolate कर देगा ना. See, the voltage will be same. There would be some input resistance of this circuit, right? But effectively, if you put this op-amp, it will isolate two devices, and there will be no effect of this circuit on this or this on this. See, there is a circuit here. There is a circuit, right? From where you are getting some output. And here you want to cascade these two circuits because for some application. But when you feed this input, this output to input of this without using op-amp, it will be not isolated, right? Because feed this input resistance is very high. So this is a block, correct? This will work as a block which will isolate these two entities. इतना समझ लो अभी, ठीक है? So this is one application of using. This is a buffer, right? But it will isolate both the circuits. The effect of first circuit would not change the parameters of the other circuit, ठीक है? So for isolation purpose, you can use emitter follower. Next is, let's solve one numerical example, which is of interest to all of you because it will come to the exam. So you have a op amp, you apply a power supply of plus minus 15, bandwidth of this op amp is 7 hertz, and the output swing is plus minus 13 volt. Okay? Now we provide the voltage series feedback, R1 of 1 kilo ohm, RF of 20 kilo ohm, and this is also the property of your op amp that the gain is 3 into 10 to the power 5. Correct? Or 2 into 10 to the power 5, whatever you get. So you have to derive what is the voltage gain with feedback, input resistance with feedback, output resistance with feedback, bandwidth with feedback, and output offset voltage with feedback. Total output offset voltage with feedback. These are the 5 parameters you have to calculate. How would you do that? It's very simple. A is given to you. B is your feedback circuit gain. Correct? This is your feedback circuit gain. 1 upon 21. What is the value of B? Calculate करो please. One of. This is a very important numerical, right? Though it looks easier now, but when you forget the things, it will become difficult. 1 upon 21 is? Open loop voltage gain is given to you. Feedback circuit gain you can just evaluate. What is 1 upon 21? 0? 0 point? 0.6. And what is your AF exact is A upon 1 plus AB. So before deriving this, just evaluate 1 plus AB. AB is your loop gain. So 1 plus AB is, because this is a very important term, 1 plus AB. कितना आ रहा है? What is the value of 1 plus AB? So for numerical point of view, you will first evaluate 1 plus AB, because this is the factor by which each of the parameters either get multiplied with or get divided with, right? 1 plus AB is जो भी है पॉइंट में आएगा, right? It will be in points. Please, anyone who has calculator? Rahul, do you have calculator? Huh? 7 is minus 5. 14 टू नहीं नहीं इतना नहीं होगा into 10 to the power 3. So you'll see that your AF would be divided by this factor. Your RIF or the input resistance will get multiplied with this factor. Your output resistance will be factored by this value 1 plus AB. Your bandwidth would get scaled by this factor. So just evaluate 1 plus AB and you can see. Next we'll see VOOTF. वो थोड़ा सा different है. Different नहीं है. So what would be your output offset voltage for the open loop condition, right? You have not applied any feedback. There is no input. What I mean, for electrical engineers, your op-amp is this. If you want to study its electrical properties, for you op-amp IC is this. Correct? So at the output, we see some voltage even though there is no input at V1 and V2. Correct? So that is called output offset voltage. This is one electrical parameter or electrical property in output offset voltage. Correct? So let us say X is the voltage difference which appears even though you are not applying any input. Correct? So at output, what will you get? A times X. Correct? A times X. So even if X is very small in microvolts, A is very high, right? Most of the time it will be more than V saturation because your voltage swing allowed is plus minus 13 volt. Correct? See, this is the input output characteristic of your ideal amplifier. Input means VID, output is V0. Input output characteristic या transfer characteristic बोलते हैं ना शायद of ideal op amp. Just check it once. I would call it input output. You apply VID as input. This is the ideal scenario, right? Practical scenarios. By A is infinite now. It's the slope. Correct? For ideal scenario, it should be something like that. Good. So, anyways, so even if your X is very small, you will reach to saturation. Correct? और अगर practical scenarios भी हैं तो ये this is very steep, very steep. Correct? So even your X is in microvolts. You have seen this in one of the numericals, right? So your output offset voltage can be assumed as plus minus V set. ठीक है? Anyways, then we have seen that after feedback, your output of voltage is get scaled by a factor of 1 upon 1 plus AB, right? Or get divided by a factor of 1 plus AB, which you have evaluated. And this is plus minus 13 volt because this is given in your question that V out swing is plus minus 13. Swing is the maximum value or the minimum value at the output which is allowed, right? Which is this only. V set and minus V set. plus minus 13 and whatever factor we call it k, so you would divide it by factor k. Correct? Please repeat this numerical for the voltage follower case. कैसे करोगे? बुक है तुम लोगों के पास? नहीं है? नहीं, अभी कर लेते. So voltage follower means AF should be equal to 1. What is B? Where is the circuit for voltage follower? Yes. This is the voltage follower, right? This is the voltage follower. This is your VF and this is your V0. Correct? So capital B is 1 because V0 equal to VF. What is our aim? When we solve this example, we have seen that we need to find out this quantity. Correct? And it is given that since it is an emitter follower, voltage follower, AF should be equal to 1. We have seen that we are directly connecting your output with the input, correct? So B will be equal to 1 and A is given to you 3 is to 10 to the power 5, or 1 plus AB we have already now. So 1 plus AB will be different now. So it would be 1 plus 3 into 10 to the power 5. So accordingly you can see that, but AF is 1 second. You have to see A upon 1 plus AB. So 1 plus AB is almost equal to 3 is to 10 to the power 5. So this we need not to worry. ऐसे भी निकालोगे तो सेम ही आएगा 1 plus AB. So only this K value is almost 3 is to 10 to the power 5, which is almost equal to A. So bandwidth would increase by a factor of A. Good. 1 plus AB is almost equal to A, right? So this is the main finding of this, that 1 plus AB is almost equal to A. So that is why it is called a special case, right? Because we are assuming B equal to 1. So A would almost equal to A. 1 plus AB will become almost equal to A. That is why it is called a special case of your non-inverting amplifier. And one such application we have briefly explained, maybe not in fully detail, but you can see that book, Sadra Smith, for details, right? Why do you need something in between two circuits, right? और VOT में क्या आएगा? व्हाट वुड बी द वैल्यू ऑफ VOT? प्लस माइनस 13 डिवाइड बाई A. So next is the voltage shunt feedback amplifier using op-amp. We'll see this circuitry today, which is also known as inverting amplifier. Just look at the circuit. Is it visible? So this is the voltage shunt. So you have to take the voltage and you have to put it in series with the Vin. Correct? You are familiar with this. You are very familiar with this, right? If you see it very carefully, you will see that this is nothing but an inverting op-amp. देखो, please get this book because few of the things are very similar. So it is not possible for us to repeat the same things. Like for example, in order to derive the same formulas which we have derived for voltage series, you can use the book and see, right, and discuss the differences. Correct? If there are some subtle points we can discuss, but not the whole derivation, right? Because it will again take 2 classes. Because if we do the same thing for this, as exercise, you have to find out what is the closed loop voltage gain AF, right, for this configuration, and everything is given in the book. Ideal scenarios, it is simple, right? It is called the virtual ground concept. How many of you are aware of that? See, for the ideal cases, your V0 is A times VID. VID is, so A is infinite, VID is V1 equal to V2, not 0. Sorry, VID is 0, so V1 equal to V2. It means if this is ground, this will also appear as ground. That is why it is called virtual ground. कुछ लोग अपना बात कर रहे हैं मोबाइल में. So yes, by using virtual ground, you can easily evaluate the ideal condition. So that is, I think, third point. First, discuss the concept of virtual ground, right, and then derive AF ideal. First is a bit tricky. देखना book से. This is easy. Once you have this, you can apply KCL, KVL, and see. You have to just see what is the voltage here. Correct? V0, V, and what is voltage here. You can take help from this circuit. क्या होगा बताओ? यहाँ 0 है, so 0 will be here. Here you have V0. So the current which is flowing through it is V0 divided by RF. Current which is flowing here is almost 0. This is 0. This is 0, so you can think that it is connected. And V in is the voltage across this. So current is I in is almost V in divided by R1. So V in divided by R1 should be equal to, because this current is very small, V0 divided by RF. नहीं यहाँ के I माइनस भी होना चाहिए, right? So V naught is minus RF by R1 into V. Right? Most of the time we discuss this. I mean, in many places. This is first you study the concept of virtual ground, which is we have just discussed. So AF ideal we have evaluated. This point we have done. You have to see how to evaluate the closed loop voltage gain exact, and then feedback gain of the feedback circuit. So it is quite easy. Just read the book. What is the feedback? VF, right? VF. And this is your V naught. There will be some voltage drop here. And you have to evaluate what is the relation between V. So you have to see gain of the feedback circuit is VF by V naught. ये करना. This you have to do. Then you have to find out what is the input resistance with feedback, output resistance with feedback, and bandwidth with feedback, and total output offset voltage with feedback. Offset voltage with feedback. So this will be up to this point. You have to submit as an assignment along with the और assignment दिया क्या? Yes, the output, because see once you read this now वो similar है, so just this is two assignments. Then we will discuss this. Similarly, as we discussed the special case of non-inverting, that was voltage follower. You have inverter and current to voltage converter. Do it, and we'll discuss if you have any problem, right? मैं quickly या फिर I will just quickly go through everything. ठीक है? But not in detail. So you just prepare your assignment first, and Sunday will be the last date. या फिर चलो Monday का. Till Sunday you have something, right? Okay, we'll see.